Welcome back to the deep dive. Today, we are absolutely refusing to talk about prompt engineering in the way you usually hear about it. No, we are not talking about asking a model to act as a senior developer or the magic of saying take a deep breath. We're looking at the infrastructure layer. We're talking about the brittleness of the entire stack.
It is, I mean, it's the single biggest headache in productionizing LLMs right now.
Rare.
You spend a week, maybe more, tuning a prompt for a RAG pipeline, you finally get the F1 score up,
Right. You think you're done.
and then you change the underlying model from GPT-4 to 4.0, or you just tweak the temperature by 0.1, and the whole thing just collapses. It's gone.
It's not engineering, it's parameter roulette. But, okay, we have a paper on the desk today from Salesforce AI Research Promptomatix that claims to solve this. And they aren't just offering another playground. They're proposing a zero-configuration, automated optimization framework.
And look, zero configuration is one of those marketing terms that, usually sets off my alarm bells.
Mine too.
But what they're actually building here is, well, it's a compiler. They're trying to move us from handwriting assembly code, which is basically what prompt engineering is right now,
Yeah.
to a managed workflow, a real compilation workflow where you just define the intent and the system handles all the instruction logic.
Okay, so that's the mission for this deep dive then. Let's see if that claim actually holds water. We're
Right.
going to tear apart the four-component architecture. We will look at the specific math they use for cost-aware optimization. That's equation 1 for those following along in the paper. And we absolutely need to have a serious conversation about their synthetic data pipeline. Because if algorithm 2 works, this changes how we deploy everything. If
Yeah.
it doesn't.
Then it's just a very, very expensive wrapper around DSPy.
Yeah.
And we need to figure out if this automation is actually robust or if it's just shifting the complexity from the prompt to like a meta prompt.
Exactly. So let's start with the architecture. They've broken this down into 4 components: configuration, optimization engine, yield, and feedback. But let's look at the configuration component first. This is where they claim to solve the cold start problem.
Right. And in a traditional setup, let's say you're using DSPy or even just standard few shotting, you have to define the schema. You have to sit there and type out input is context, output is answer. You have to curate all the few shot examples by hand.
That is the barrier to entry. It's a ton of work.
And Promptomatix just says, don't bother.
Really?
Essentially, yeah. They use what they call a teacher LLM, specifically something powerful like GPT-4o or Claude 3.5 Sonnet, to just parse your raw natural language intent.
So it just reads my mind.
It tries to. It analyzes your input to infer the schema. It looks for little markers like task or rules, but if you didn't include them, it hallucinates. Or to be more generous, it infers a structured format for you.
So it's doing the metaprogramming for me. It's deciding, okay, this looks like a sentiment analyzer, so I'm going to need to construct a signature with a text input and a sentiment label output.
Exactly. But this is where the architectural choice gets really interesting.
Yeah.
They don't just shove everything into one single pipeline. They actually built a dual backend system. There's the simple meta prompt backend, and then there's the full DSPy backend.
Okay, why split it? If DSPy is the gold standard for structured compilation, why would you even bother with a simple version?
Latency and cost. DSPy is incredibly powerful, but it's heavy, it compiles, it optimizes, it runs teleprompters. That all takes time. The simple metaprompt backend is designed for when you just need a good enough optimization in, say, seconds, not minutes.
It's the lightweight option.
Yeah, it effectively just asks the teacher LLM to rewrite the prompt based on a few simple heuristics. It's quick and dirty.
But for us, for the listeners tuning in, we care about the heavy lifting, the DSPy integration.
That's where the real power is, of course. They're using DSPy's MIPO v2, the multi-prompt instruction proposal optimizer. And this is a full-on Bayesian optimization approach. But Promptomatix adds another layer on top of it, adaptive module selection. This is equation 2 in the paper.
Okay, let's unpack equation 2, because usually when I'm using DSPy myself, I have to pick the module. I have to make the call. Do I want dspy.predict? Do I want dspy.chainofthought? Maybe program of thought. And if I pick wrong,
Your performance just tanks.
yeah,
And picking right is genuinely hard. You might think chain of thought is always better, but for a simple classification task, it just adds latency and a ton of token cost without actually improving your accuracy.
so how does Promptomatix automate that decision? How does it know?
They treat it as a probabilistic problem. Equation 2 basically calculates the conditional probability of a specific module performing well, given the task type, the complexity, and whatever few demonstrations you provided.
So it's the teacher LLM basically saying, I see you're doing math word problems, and they look like GSM-8K style problems, so I know from experience that chain of thought usually gives a 40% lift here. I'm locking that in.
Precisely. Just think about the search space. If you try to run a grid search on every module type against every single prompt variation, you'd burn through your entire API budget in an hour.
Oh, easily.
Equation 2 is a pruning mechanism. It uses the teacher model's existing knowledge, its priors, to narrow that search space before the really expensive optimization loop even begins.
That makes a lot of sense. But even if you pick the right module, MIPRv2 still needs data to optimize. It needs a training set. If I'm coming in with zero configuration, I don't have a labeled data set. I just have a vague idea.
And this is the data bottleneck. This is the single biggest point of friction in prompt engineering today. And this is where I think the paper takes its biggest, most ambitious swing with algorithm 2. The synthetic data generation pipeline.
Okay, walk us through this. Because synthetic data is often just a polite way of saying low-quality garbage.
It often is, yes. Promptomatix tries to mitigate that risk by treating data generation as a 4-stage pipeline, not just a single prompt call.
All right, so step 1.
Template extraction. It takes your tiny input description and derives a rigid structure from it. Then, batch generation. And they don't just blast the LLM. They intelligently manage the token limits to maximize the throughput. But the real magic is supposed to happen in step 3, diversity optimization.
How are they defining diversity here? Are they just, cranking up the temperature and hoping for the best?
No, and that's the key. Simply raising the temperature just gives you randomness, not actual coverage. They explicitly prompt the generator to cover the latent space of the task. They ask for different input lengths. They ask for different linguistic styles. They specifically ask for edge cases.
Like sarcasm in a sentiment analysis task or ambiguous queries in QA.
Exactly. So instead of getting 100 examples that all look like the product was good, you get a distribution that actually looks a bit more like the messy real world.
That's the goal, anyway.
That's the goal. They're trying to force the synthetic distribution to match the variance of real production data. And then finally, step 4 is just filtering. They use the teacher model, again, to validate the examples it just generated.
Okay, but let's play devil's advocate here. This is the circular dependency problem, isn't it? You're using a teacher LLM, let's say it's GPT-4, to generate the ground truth data for a student LLM to learn from, and then you're probably using that same GPT-4 to judge the result.
It's turtles all the way down.
Yeah.
You are absolutely right to be skeptical. I mean, if the teacher model has a bias, for example, if it refuses to answer certain questions or if it has a preference for verbose, really flowery language, that bias gets baked right into the synthetic data.
And then the optimizer sees that data and thinks, aha, success looks like flowery language. So it optimizes the prompt to produce more flowery language.
And then the judge model, which again is also the teacher, sees the flowery output and gives it a high score. You've just created a self-reinforcing echo chamber. This is the real danger of zero config. If you don't have a human in the loop to sanity check that synthetic data, you might just be optimizing for the model's own narcissism.
The paper makes the argument, though, that imperfect synthetic data is better than no data at all.
And in a cold start scenario, I think I agree. It gets you from 0 to, say, 80% pretty quickly. But for that last 20%, for true production hardening, you cannot rely solely on algorithm 2. You have to inject real, human-labeled ground truth eventually.
Okay, let's move to the optimization engine itself. They have the data, they've selected the module, now they run the optimization. But they introduce a constraint that I found really interesting for anyone who's actually paying the API bills: cost-aware optimization.
Right, this is equation 1. And this is where they really diverge from a lot of standard academic papers that only care about getting the highest possible score. They define the loss function as L equals L performance plus lambda times L cost.
Standard regularization. But look at how they define L cost. It's not linear. It's an exponential decay function.
Yes.
I have to stop you there. We're talking about an exponential function just to save a few tokens. That feels like over-engineering. Why isn't a simple linear penalty enough? If I charge you a penny per token, the cost is linear, right?
The financial cost is linear,
Yeah.
yes, but the information value isn't. And that's the core insight here. Think about it. A linear penalty is just a blunt instrument. It punishes a long, necessary explanation just as hard as it punishes a long, rambling hallucination.
So if the prompt needs to be long to be accurate, a linear penalty might just kill it before it has a chance.
Exactly. You'd end up with a very concise prompt that just doesn't work. The exponential decay creates a kind of soft cap. It allows the model to prioritize performance and use as many tokens as it needs up to a certain point. But as the prompt gets bloated, As it drifts into redundancy, that penalty curve goes vertical. It aggressively prunes the fat while protecting the muscle.
They did a sensitivity analysis on this lambda parameter in Table 2, and the results are pretty dramatic.
They are. At lambda equals 0, so ignoring cost entirely, they got the highest score, 89.08, but the prompt was just massive, 29 units of length, whatever that unit is.
And what about at lambda equals 0.05?
The prompt length shrank all the way back to the baseline, around 11 units, but the performance collapsed down to 84.83. It effectively killed all the gains from the optimization.
So they found a sweet spot somewhere in the middle.
Right. They argue for lambda equals 0.005 or 0.01. This retained 99.9% of the performance, but with a significantly reduced token count. And look, for a high-throughput API endpoint, that reduction is pure profit.
So the big question, does it work? Let's look at the benchmarks. They compared Promptomatix against a manual zero-shot, something called Promptify, and Adelflow.
The headline numbers are definitely strong. On Squad 2, the QA task, Promptomatix hit 0.913 compared to a manual zero-shot at 0.860. On GSM-8K, the math task, it jumped from 0.475 all the way up to 0.732.
Though Adelflow did edge them out slightly on math at 0.767.
Adelflow is a formidable framework, you're right. But the most telling result for me wasn't the win. It was the failure mode of the competitor. You have to look at the XSum summarization task.
The Promptify row. It completely collapsed. A score of 0.177. That's basically random noise. What happened there?
That is almost certainly a misalignment in the few-shot selection. Promptify probably selected examples that just confused the model. Maybe they were too long, or the style was wrong, and the model just started hallucinating or outputting complete garbage.
And Promptomatix held steady at 0.865.
Which suggests that their configuration brain, that whole initial step of inferring the schema and using the teacher to validate the setup, it makes the whole process much more robust. It prevents that kind of catastrophic misalignment.
I have to be the skeptic on the evaluation metrics, though. They used automated metrics BERT score for QA, exact match for math, and they only averaged 2 independent runs.
Runs, yeah.
In the age of stochastic LLMs, that feels, well, it feels statistically thin.
It is thin. We all know GPT-4 can vary wildly just based on the seed. A really robust paper would usually show confidence intervals over 5, maybe 10 runs. So while the improvement is large enough that I believe the effect is real, I wouldn't take those specific decimal points as gospel.
Okay, now let's talk about actually putting this into production, because this whole optimization process sounds expensive.
Oh, it's incredibly expensive. I ran some back-of-the-napkin math on this zero-config workflow.
Yeah.
You're calling GPT-4 to read your mind. Then you're calling it, maybe 300 times to generate all that synthetic data. Then you run MIPOV2, which might run 30 trials of the student model. Then you run a judge model to evaluate all those trials.
That is a lot of compute just to write a single prompt.
If I tried to expense this for a weekend hackathon project, my CFO would have a stroke. This is not for small tools. This is for high-volume production-grade endpoints, where saving 10% on tokens or gaining 5% in accuracy actually translates to thousands of dollars a month.
The paper does acknowledge this as the research gap. The overhead is high. But they do offer a way to manage the life cycle, stateful sessions.
And this is a crucial feature for the user experience. Optimization shouldn't just be a black box script you run once and pray. Promptomatix saves the state, the synthetic data, the failed trials, the metrics, all of it.
So I can actually open it up and see why a certain prompt failed.
Exactly. And you can interact with it. They support granular feedback. You can highlight a specific section of the optimized prompt using start and end offsets and literally say, this part makes the tone too aggressive. Fix it.
So it's not just auto-optimize, it's more like auto-optimize, then let the human refine.
And if you don't provide that feedback, they have an auto-feedback loop where a reasoning-heavy ModelThink O3 or GPT-4 in judge mode tries to diagnose the failure on its own.
It's an automated red teamer.
Effectively, yeah. It closes the loop.
I want to zoom out and look at the limitations here. They mentioned they don't support multi-turn dialogue or multimodal tasks yet.
Which, that's a significant limitation in 2026, isn't it? Most complex agents are multi-turn. If Promptomatix can only optimize a single-shot request response, it's missing the entire complexity of agentic workflows. You can't optimize a React agent just by optimizing the very first prompt.
But looking at their future work section, they seem to be eyeing an integration with RLHF and DPO.
That's the logical next step. Instead of just rewriting the prompt text, you could use that synthetic data to actually fine-tune a LoRa adapter. If they can bridge that gap from prompt optimization to lightweight fine-tuning, that becomes a very, very powerful platform.
So, to summarize the findings here, Promptomatix is a sophisticated, maybe even over-engineered wrapper around DSPy that dramatically lowers the barrier to entry. It seems to work. It handles the math of cost optimization elegantly. But it comes with a high upfront compute bill and the very real risk of synthetic data bias.
That's a very fair summary. It really represents a shift from prompt engineering as an art form, tweaking words like a poet, to automated prompt optimization as a managed engineering workflow.
And we need that. We can't keep hand-tuning prompts for 100 different microservices.
No, absolutely not. We need compilers for prompts. Promptomatix is, it's an early but very promising version of that compiler.
So for the listener who is about to go try this out, or maybe try to build their own version of it, what is the one thing they should absolutely watch out for?
Watch the lambda, that cost parameter. The paper suggests 0.0005 is the sweet spot, but that depends entirely on your specific model pricing and your latency requirements. Don't just trust the default. You have to run the sensitivity analysis on your own task.
And please, for the love of clean data, look at that synthetic data set before you let it train your production model.
Trust, but verify, especially when the thing you're trusting is a hallucination engine.
I want to leave you with one final thought to chew on. We're building these systems where the teacher model determines the strategy, it generates the data, and then it judges the final result. Are we actually optimizing the prompt for the task? Or are we just training models to be really good at talking to themselves?
And if they get good enough at talking to themselves, do they even need us to listen anymore?
On that slightly existential note, thanks for listening to The Deep Dive. We'll catch you on the next one.